All right, so I was planning to go a little bit longer than 20 minutes, so I'll probably rush through this a little. The sort of the overall message of this presentation is about, we've talked about individual models and workflows, and yesterday we also touched a lot on composability in the case of what GlimateModels is doing. We need to talk to that as well, but from a somewhat different perspective, because in what we do, as you've already heard, there's a lot of files and fairly long calculations. So the composability often comes with like, okay, I'm going to download one data set and I'm going to do a simulation, I'm going to save this and blah, blah, blah. So it's going to feel different. But this is sort of, I think, where we are in building kind of a composable ecosystem to make more complicated workflows in Julia, at least in my case. Alex also talked to that before, and the other Alex as well. So I'll say a little bit more about ClimateModels and MITgcm GL as promised, and then I'll get to the Climatology GL side of things, which is really on the data. I've already shown this. ClimateModels GL is a general interface that's really using files as a kind of a beginning point and an end point. It integrates various models that you can run that are somewhat light, MITgcm in particular through MITgcm GL. I've already said this, there's interactivity coming from Julia. I wanted to illustrate a little bit what the interface is in practice. It consists for a given model, giving it 3 methods. One is called setup, the second is called build, and the third launch. With a shortcut, which is just run. So ultimately, you take one of those models I've mentioned, you do the first line here, which is defining a data structure and kind of telling you what the model actually is, and then you do run model, and you're done. So that's the goal, is to have some kind of 1 line, 2 lines, I guess, workflow. Setup typically is I'm going to deal with files, I'm going to choose a configuration and so on. The build, in the case of a Julia model, well, that happens on the fly, so maybe there's not even a build step, right? It's just like once you instantiate it in memory, it just happens for you. In the case of MITgcm, there's an actual, Fortran compiler that kicks in. And launch is really either run the thing, like do the calculation, or send it to a queuing system when it's bigger. What you see at the bottom is the run directory at the end of this, where you will find the output files, and then this log folder, which is where I keep track of the workflows. Here's a slightly different example where I do 2 simulations. So again, the first one defines a model, and this is this is a very, very simple model. This is like a random walk in Julia, so it's like a single function written in like 1 line. But it's just to demonstrate the strategy. Oh, my laptop is about to go down. Sorry, I need to check on, okay, I have 10%. That will keep us on time for lunch. Okay. So here what I do is I do the same simulation, okay? There is 100 step, and then want to modify that, do twice as long. So I change this in memory in Julia, right? That's one of the idea of this framework, is to expose the runtime parameters and the ones you care about out of the gazillion we might have. In memory, in Julia, you just change them and you hit run again, essentially. Through this put and launch method. And then there's this log function. So what happens with the log part is each of those steps is put into a Git subfolder called log that you can then retrieve afterward to know what you've done and to make the different workflows reproducible. So here you see that originally we did the setup, we put all of the parameters in a TOML file, built our sort of project, and then yeah. Oh yeah, thank you. Oh, this is great. You should be able to, yeah. Thank you. Thank you so much. So the point of this is, this is a very simple case where arguably there's a bit of an overhead with all of this, right? But often when we do modeling, we kind of explore things, we make decisions, we, trial and error type of thing. And so with this, I'm able to record that in an easy way, share it with somebody else, and that's meant to make my workflows reproducible. The same thing happens with a bunch of different models. Like I said, we don't always run the models. Right? In the case of IPCC models, for example, there is something that a lot of people do, which is I'm just going to get the output and do my calculations with that. I tend to call that the replay mode of climate and ocean models. And so that's why this fits right in. Of course, there is no build at this stage. So this is an example from the Climate Model Archive. I have built this sort of things for various models in different languages. Here is an example of a fast emulator of a big climate model. This one is called Hector. That's been created in C++ and sort of trained on the big models. But it's kind of nice because you can create scenarios like this, which can then become part of your workflow. So for example, what I would do with this is I create a future scenario. I can combine it with an existing ocean model solution and make predictions and kind of downscale to make scientific analysis. So that's ClimateModels in general. I just want to give you a little bit more of a flavor. I've done some presentations before on this. Here is a little bit more detail on MITgcm GL. So on the left is the, I guess, 3-line version of my running a GCM in Julia, in the case of the eco solution. So these are not the high-res models we've seen. It's the 1-degree configuration of MITgcm that we use for the reanalysis. That runs on like 96 cores over 12 hours or something. The 3 lines on the left, that's just running the default, right? The reason I'm showing you this is mostly to show you the right-hand side. So the right-hand side is, using MITgcm, blah, blah, blah. The first 3 lines is the same as before. Forget for now what's in the boxes, then setup, build, and launch. So same as exactly as before, but the reason I'm showing it is these boxes in the middle where we're not going to modify what MITgcm is doing. For example, we are going to say, well, I've already built this thing, so I don't need to recompile every time. So I can provide the link to the executable. I have a lot of input folders, like the same as Simone was telling you about. You need a bunch of forcing fields and a bunch of bathymetries and stuff. You don't want to download that every time. So typically you download them, you put them somewhere, and you just specify that. Then, you might want to modify the model runtime parameter. So not everything in a big model is changeable, right? You're typically not going to change the way that you discretize the world every time. That's kind of hard-coded. But there's a lot of things that are changeable at runtime, both in something like Oceananigans and something like MITgcm. And so this is an example where I'm turning off a module. So those lines are all commented, but you uncomment them, and now you have an interactive way of making new solutions. I'm going to skip this, but I guess what this will point you to is a bit more of a detail on how the different configurations are kind of encoded in Julia. That's the first thing. But the way that I'm dealing with all of my runtime parameters, this sort of monolithic thing leads to, I guess I'll show you this one. Right. So these are all of my runtime parameters that I change in this particular model. Right. This specifies all of the output and so on. So it's a long file indeed. Could calculate monolithic, that'd be okay. At least it's a TOML file now. It used to be this kind of custom, annoying format that we had. So now I'm dealing with this way, And then the other bit was, ooh, where did this go? No. No. There we go. The last thing is, so MITgcm GL generates a submission script for you at this point if you're going to use a queuing system. And so that's how you don't have to interact with that either. I'm going to skip over. The composability of this, I've already talked about. Here is an example where we run MITgcm in an atmospheric configuration, and then on top of that, after that, we run a particle tracking simulation. Let me talk about the data side of things. So ocean modeling, in my mind, is mechanistic models, like the ones we just talked about, that have equations encoded in them and then simulations. But a lot of ocean modeling is also applying statistical methods and building statistical models or empirical models and training surrogates and all of that stuff, right? And so that's where you really want to start to have like input and outputs and deal with a lot of data sets. So I'll show you a couple of those workflows that I've been building with the same tools as before, but then adding data and adding different things to it. And they're rooted in my science, as always. So I'll go and refer you to this first example. So there is a warming of the ocean that's going on over the past decades. The second project is also about that. Here you're looking at, as a function of time and latitude, the change in SST, sea surface temperature, over 40 years. And you see this gradual warming all over the planet. The top is what data set that is from satellite. The bottom is one of my climatology MITgcm-based estimates. And so one of the reasons that we want to use mechanistic models is ultimately we want to attribute these kind of things. So we want to have heat budgets. So that's why when I do analyze these topics, I start from something like echo MITgcm that has a heat budget where the terms add up to 0. So in this plot, you're seeing the net change in temperature, essentially, in blue, for the layer between 0 and 200 meters. It's called ocean heat content because it's integrated, so it's in weird units, but essentially the change in temperature over that layer. The orange line is what comes from the atmosphere, and the green line is what crosses 200-meter depth. So that's what you need to have to be able to explain what's going on in the blue line. If you don't have those terms, and you just have temperature, we really don't have a good insight into the processes. So I always start from that, but then I want to make sure that I'm on track with observations as well. So that's when I bring in Argo again. This data set that I was telling you about is the key to monitoring ocean heat content. And so here is a comparison that just shows that the red line is kind of in agreement with my blue line, which is what's on the left-hand side from the model, or the mechanistic model. So that's the first thing. And then it does show that over this 0 to 200-meter layer over the past 20 years, there's indeed an increased accumulation of heat. So now we have a mix of different models that lets us really probe the behavior of the real system with some mechanistic understanding. Here's the workflow around this. And that's where it becomes really, building blocks and like accumulating steps that, some of them take a fair amount of time. So first off, I started with a 20-year solution, so I wanted to extend that to more like a 60-year solution, so I get an entire atmospheric analysis. For this, download that, put that on some file folders. Then I'm going to use this to modify my solution and extend it in time. So these are the next two lines. I'm going to apply a first adjustment, which is because the model has run longer and was less optimized, it has drifted. So I'm recalibrating in the timing towards echo, which is the reanalysis, the ocean reanalysis I was telling you about. And then I did two more corrections, or adjustments. One, and they're both based on Argo and geospatial statistics of them. One is climatological and the other one is time variable. And I'm presenting all of this to you because that's where I wanted to get to, the geostatistical part, which relates to a lot of what we talked about. So this is what I do. I have my sparse data sets, Argo. I compute misfits, and I'm going to map the difference between Argo and the previous estimate, the intermediate step. I split up the world into boxes like this. So there's 30 of them in this case. That's the first level. You don't see the 30 of them because it's kind of a bit hard to read, but there's 30 of them. Then I do the same thing at twice the resolution. So here is, I've kept the color bar at 30 to see the increase in resolution. So this is my level 2, and I keep going like that. I keep making smaller and smaller boxes. So this is my level 9. If I only show you my 9th level of the multi-grid approach, if I just show you the first 30. In reality, there is like, this point, something like 510 to the 5 boxes. So I'm computing these statistics, these sample means, like at varying resolution going down, and then I bring everything back, and I combine them into one big map. The Lancy mask is what? Oh, yeah, so that's because I do some interpolation for the plotting. Because it's on my weird grids that I was telling you before. The boxes? Well, it's pretty flexible. What I do is I start with, separating ocean basins, because I don't want to mix up, say, across the, the Pacific and the Atlantic, across Central America or something like that. And then I can choose whatever I want. So what I'm doing right now is pretty simple, but ultimately you can think about combining more like physically based, using the geometry of the gyres, things like that, and then downscaling with just basic ranges. But so I thought I would show this because it sort of it links to some of the discussions we had earlier in the week, and I'm hoping to engage some of this community in helping me advance these sort of things and make them faster or better, and that's kind of where I was. So that's one of the workflows that I've been building that is both combines a lot of different steps already, and is relying on a lot of the Julia AO kind of contributions, and we'll do more of that. So I'm hoping to get and to find some of you to help me on that. Another very related problem that I'm working on with my group is marine heat waves. So marine heat waves are a slightly different view of this warming in a sense. And you've heard of this over the past few years that we're finding more and more extremes. Or they're more intense, or they're more widespread, or they're more frequent. Some of that is a bit fudgy. So when you say increasing, there's some scientific discussion to have. But so it starts from this kind of a map of SST. This is the anomaly in sea surface temperature from satellite. And you see these big red blobs. That's what we're talking about. So the goal is going to be to isolate those things, track them through time, understand why they occur, and how they might evolve in the future based on our mechanistic understanding. But along the way, there's a lot of data analysis. And so the first thing is a time series bit. You take a time series like this of these SST anomalies where we've subtracted the climatological mean for every month. And you see that the red is above a certain threshold. We're passing it more and more. So here, this was a marine heat wave, maybe, and now we have a lot more. So we start with that. And then, well, if you do that everywhere, you're going to find patches. And now you're going to want to keep track of those. Oh, this is not the right slide. Sorry. Oh, okay. Well, that slide never materialized. Sorry. It must be the wrong version of this talk. So in brief, the workflow looks like this is step 1 and step 2. Step 3 is this. You go from that to a polygon. And this is where something like geometry ops comes in. Then you want to do this sequentially for like every day. You want to overlap the polygons, decide if they are the same event, build a kind of a time variable moving polygon. Once you have that, then you can start studying it. So it's the state of affairs. I wanted to show this because I'm going to need help on that as well. But it's already been great to be able to leverage the Julia ecosystem for this. And I think we are going to do very nice things in this field. It's a nice use case to work on. If you're interested in contributing, please reach out. And since it's lunchtime, I'm going to go very briefly on this slide just to say there's still a need to consolidate the kind of the data accessing and handling ecosystem that we have. There's a lot of nice things that have been done to a large degree by this community. Things like the StackGL, for example, is very useful. I've created this Dataverse.jl package that interfaces with a data archive for now through its API to download and query, but then we should be able to push it as well. So the idea is, at the end of your workflow, when you have your data set, you want to push it to an archive like that, put a DOI on it, right? And then your user needs to be able to download it automatically. So that's what Dataverse.jl is. I don't have time to talk about all this, but that's a very interesting project. I'm always, excited to add more models to the ClimateModels.jl sort of world of things. Typically means, taking shenanigans with the kind of API you have and bringing it back to the kind of APIs you don't like, that I do, but that a lot of people know. So I think it's a useful thing to do because it exposes the models that are innovative to the community that is not quite used to that, but it's an easy entryway to them. And it makes everything kind of interchangeable, such as, when I want to use ClimaOcean, instead of MITgcm, I don't have to think about the APIs. At least I have a first way to do it. I was pretty excited with the talks on emulators, and so I have 2 candidates here that I think are ripe for putting into the Julia Sim world, and that I've listed. There was also some very interesting stuff that I learned this week about existing interfaces to models, these FMIs and BMIs. And the last thing down my list is I'm still hoping we integrate more this kind of view of the geospatial analysis that's standard with the ones that we have in our sort of ocean modeling world, which, as you saw, has these weird kind of grids that don't necessarily always fit into the pre-existing models, but I think there's a lot to gain by tightening that up. And so if you're interested in that, please talk to me. Enough from me. Thank you for your attention. Sorry if it was a bit rough around the edges, these presentations. And if you have questions, please ask them.